So in this video, we'll talk about how to find the derivative of some sort of exponential function. So in this case over here, our exponential functions are always going to use a base of e. But why are we using e? What's the case with this number? Now we know e is approximately 2.72, just the two decimal places. There's a lot more, but I mean, we're not going to go into that. But what's special about this number is that if you were to draw, let's say, some sort of graph of just e to the x, this one over here is going to look something like this. So as you may know, that the exponential function goes way up as x goes towards the right, and as it goes towards the left, it just, well, it hits an asymptote of y is equal to 0. Now what's special about this function is that Euler found a number where if you have it to the power of your horizontal axis x, you found that this exact same curve actually represents the gradient of the blue line. So it's able to find out that in the end, you're going to have, let's see, if you differentiate e to the x, then you're actually going to end up with e to the x again. So using that as a starting point, he realized that you can actually do a lot more of that. What you can do is, if you change the index over here into, let's say, k to the x, oh sorry, not k to the x, kx, so if you multiply by something there, finds out that this k over here can actually just be dropped down to the front as the coefficient. So what's happening over here? Now, this is very clear after using the chain rule, which we probably haven't dealt with for now. You'll see in more future videos about how to use the chain rule. But in the end, what you can use as a more general definition of your exponential derivative is that if you have e to the power of some sort of function g over here, then what you can do over here is you can grab the derivative of g. So to imagine that you got the derivative with respect to the variable inside, so d dx, the derivative of g with respect to x, take it to the front, and this g to the x will stay the same in both. So we're going to keep the index from the original function to the original function to the derivative function. So these two are going to stay the same, but what goes in front is simply the derivative of what's on top. And you can see the same thing is happening here with the more simplified rule. So if you have e to the kx, so you have now a linear function up here, then the index will stay the same in the derivative, but the only thing that's happening is we're just dropping this k right to the front. So we'll try a few examples here, just to demonstrate how we can go about using this a little bit more. So over here, we got y is equal to e to the negative 2x, and we want to find the derivative of y with respect to x. So in other words, we're going to find dy dx. So this is pretty much another way of saying I want to find f dash if you use f of x for y instead, and f dash for dy dx. So that's what it means in a nutshell. It's a bit more to it than that, but we're just going to use dy dx for this video over here. So if you want to find the derivative, so dy dx, then what you need to do is, now remember, we're going to keep this index over here. So this one over here is just going to come down, negative 2x. So we still have the same base. And what you have in front now is the derivative of negative 2x. We know that's negative 2. So that's it. This is your final answer. Okay, now over here, we have something a little bit more complicated. We don't really have kx, or at the top over here, it's now quadratic. So we need to do something a little bit more different here. So when we have dy dx, what you're going to end up with is, so we keep both the base and the index, so we still have e to the 3x squared. What goes in front over here now? We need to differentiate 3x squared. So the derivative of 3x squared is 6x. So we're just going to multiply these two together. And as you differentiate exponentials as well, you can actually just differentiate these two terms one by one. Next up we have minus 2. Keep the negative 2 in front first. And we're going to look at this one over here, e to the power 4x. So we keep e to the 4x, and we bring the derivative of 4x down to the front over here. So what's the derivative of 4x? It's just 4, isn't it? And so just to clean this up, first term stays the same, and the second term is 8 times e to the 4x. Alright, so this one looks a lot messier, but just like how we deal with the derivative of ax to the power of n, let's just change this into index form first. So I'll just use a different color for this. So a separate step here, which is pretty essential to figuring out what's going on. And a 1/3 is just the coefficient. Square root of x is x to the power of half plus 5 ex squared minus 3x. So that stays the same. It's all in index form in the index of e, and we have e squared. Okay. So over here, we have dy dx equal to 1/3. And to get the derivative of this form over here, we need to take the index to the front. So remember, this is different from exponentials. When you have x to the power of n, we want to take the n to the front, keep the x, but the index is now subtracted by 1, so you have negative half. Over here, next up we have 5. Keep the 5 to the front. What's the derivative of x squared minus 3x? Well, first of all, we do know that we can keep the e, x squared minus 3x. That all stays the same. Oops. Butterfingers here. Okay. And what we put in front is the derivative. So we have 2x minus 3. Okay. And we know that, what's this e squared over here? The negative e squared. Well, this part, it's constant. If it's a constant, then what does this mean for us? It means that this part turns into 0 in our derivative. So we're going to leave that out. And just to simplify, the expression for our derivative, we're going to get 1/6 square root of x on the bottom, since we have negative half. And over here, well, actually, you can say this is in its most simple form if you consider the factorized form to be the most simplified form. So 5 2x minus 3 ax squared minus 3x. Okay, so all of that was just differentiation. But what we also want to consider is, how can we use this to find, let's say, I don't know, maybe you just want to find the gradient at some point and you actually want a specific value to answer the question, or even the tangent equation, which we've done in the past, hopefully. Anyway, over here, we want to consider using this function over here for the next two parts. So we have half e to the 3x. We want to find the gradient when x is equal to the natural log of 2. Now, over here, if you have two questions regarding the gradient, the tangent, of course, is very closely related to the gradient at any point. we want to find the derivative function. So over here, maybe we'll use a different color for this next part, just to change it up. Okay, so yeah, maybe this will do. We have f dash equal to half. Now we're putting a 3 here, so we're taking the derivative of 3x and putting that to the front. And keeping the base and index. So we already have 3 on 2 e to the 3x. Okay, what we want to find is the gradient. Now the gradient when x equals ln2 is going to be e to the power of 3 ln2. Now this index looks quite tricky to deal with, but remember that if your base over here is the same as the logarithm base, then you can cancel them out. But before we can do that, we need to chuck this 3 over here inside our logarithm bracket. So if we do that, this part over here becomes 2 to the power of 3, doesn't it? So after we do that, so let's say this is now 2 to the power of 3, we can cancel 2 terms over here. So as long as this logarithm has the same base as the base down here, and there's no coefficient in front, cancel these out. Okay, so after that, 3 on 2 multiplied by the bracket, so 2 to the power of 3. So these two cancel out and makes this 2 to the power of 3 come down. Now 3 on 2 times 8 is 12. So that's our gradient when x is equal to ln2. Oh, actually speaking of that, this here should be ln2. Okay, so for this next part over here, we'll find the equation of the tangent to f when x equals ln2. Okay, so we've actually done half the problem here. Remember that if you want to find the equation of the tangent, what you want to use is the gradient at x equals ln2, and that's what we just found out. So we know it's 12 over here. This is gradient of the tangent. What else do you need to find the equation of the line? Well, you're going to need a point over here, so that's what we're going to find out. So for your point, you're going to sub a value back into the original f function, ln2. Okay, and f was, what was it? It was this one over here, half e to the 3x. So half e to the 3x, now x now ln2, so 3 ln2. We're going to use the same trick here, so all we're going to be doing is, just to break this down a bit, in case you didn't really get it before, is we're going to grab this 3, chuck it inside the bracket as an index, and cross these out because they have the same base as each other. And when that happens, this bracket comes to the bottom as just, well, normal number multiplied by half. So over here, you get half times 8, 2 to the power of 3, which is 4. So your coordinate here is ln2, 4. Now what you can do from here is, now you've got two of the things that you need for a straight line, or the equation of the line. You've got your gradient of the tangent and the point of which your line passes through. So from here, use either method. I'm going to use y minus y1. So y minus 4 is equal to the gradient multiplied by x minus x1, we're going to use ln2 here. And putting this into y's mx plus c format will give us 12x. Let's see, what do we have? Expanding the bracket will give us 12 ln2. And we're going to grab the 4 from the other side to get plus 4. So, having a closer look at this expression over here, we're going to see that we have our gradient here. This is our mx. And this plus c part is actually this entire chunk over here. So this is our constant, which is made up of an exact value of a logarithm and 4 over here. Okay, so just one more over here. Find the equation of the tangent. Oh, same question, sorry. This should actually say perpendicular. Or normal. Should I say normal? It's just another way of saying perpendicular. Okay, so over here, if you want to find the equation of the perpendicular line, remember that the gradient of the perpendicular line is negative reciprocal of your tangent gradient. So over here, we remember that this value over here, mt, is equal to negative 12. And so we know that mp is, oh, sorry, this is positive 12. Let's stop joking. Yeah, it's positive 12. Okay, so mp is negative 1 on 12. Okay, so from over here, same process really, because from before, we know that the point that we have to use is over here. This is the one that we use. ln2, 4. And if you just sub this back into the original equation, you're going to end up back with the same coordinates. So our point is at ln2, 4. Okay, and we can use the other method this time. Maybe we'll use y is equal to mx plus c. So we need to figure out what the value of c is over here. This is our objective. So to achieve that, we're going to sub some values into this equation over here. So what we're going to do is sub this 4 into y, and what we're going to do as well is sub this ln2, our x coordinate, into x. And of course, sorry, one more thing. And mp, negative 1 on 12, into our gradient. So putting that all together will give us 4 equal to m negative 1 on 12. X is now ln2 plus c. Okay. Oh, running out of space. Just use this part over here. So we know c is 4 plus 1 on 12 ln2. And if you want to find the equation of your line, you simply say that y is equal to, well, just this over here, except you plug in your values of m and c. So m is negative 1 on 12, x, and you want to add c, so plus 4 plus 1 on 12, ln2. Okay, there we go.